So I just wanted to clear up the energy thing with respect to relativity. And it comes from a little bit of notation confusion. This is M naught is actually rest mass, but T naught is the traveler's time, as we know. And this kind of seems to be opposite the way we think of it. So it's confusing because you want to say M naught would be the traveler's mass. And it kind of is, but it's also rest mass. So if we're standing on the ground and somebody goes by us, they're going to see their mass as their normal rest mass, but we're going to see their mass as grown. Same as the time, if you're in the spaceship, your traveler's time ticks normally, but we see it dilated because of special relativity. So there's some confusion there. Momentum is mv, of course, which would also be gamma m naught v. And energy, Einstein said, was mc squared. And this would be the total energy of the object. So if this is at rest, then you're going to have E equals m naught squared, m naught c squared. And if your particle's at rest, you can just do that, and you can have the rest energy of the object. But if it's moving, then it's going to be a little bit different, and you're going to have to say, well, it's the rest. It's going to be equals mc squared, but m is now gamma m naught, right? And what you can do with that is you can say, well, for one thing, you can say that it's really m naught. It's really mc squared, which is the total energy. It's m naught c squared, which is your rest energy, plus your kinetic energy. And so your kinetic energy is equal to mc squared, your total energy, minus your rest energy. So it's kind of like, in this way, it's a way of thinking of it where you would say the mass that you gain when you move is your kinetic energy. That's how Einstein would have thought of it. And then you can combine these two a little bit. If you square both sides of this, equals mc squared, you're going to get m squared c to the fourth. And you might think this is the end, but the m that's moving mass. And so if you kind of split this c to the fourth into c squared, you could say it's times c squared, but I'm going to add a little doodad in here and say this is v squared minus v squared. So I'm really just adding 0 so I can do it. And I do that because then I can say I'm going to take this, I'm going to multiply just this v squared out. And I'm going to say this is m squared c squared v squared. And then that's plus m squared c squared times c squared minus v squared, because these two are still left there, right? And then if I multiply that out, I'm going to have m squared c squared minus m c squared v squared. And if I pull out an m squared c squared, I'm going to have, that's an m squared. And if I manipulate that a little bit, I'm going to have m squared c squared times sorry, I'm going to pull the m squared c to the fourth, this is, obviously. And that would be 1 minus, and then I just did this to show that if you pull out an m squared c to the fourth, you're going to have v squared over c squared, because this times that is now this. Now, the reason I did all that is because this is gamma squared, right? And so if you say that, and this is still here, by the way. If you go back up and you go, okay, m is really gamma m naught, then you can say that this is m naught squared. And so m squared is equal to gamma m naught all squared. So just kind of put that in the margin, and then this becomes m naught squared c to the fourth. And of course, gamma squared is just this, right? But it's 1 over that. So 1 over this is gamma squared, and this would be gamma squared down here. So these cancel, and you end up with, and I'm going to rearrange this a little bit and say m squared v squared c squared plus m naught squared c to the fourth. And so your total energy, this being momentum, this gets us to our last, and sorry, this is E squared. So we're going to say E squared is, this is P squared, obviously, P squared C squared plus M squared C to the fourth, but this has to be rest mass here, and this is your momentum. And this is how you get to that Einstein's energy equation.